Our Sun is an average-sized star, and still, it could fit 1,300,000 Earths. The star is also 333,000 times as heavy as our planet. NASA has translated radio waves created by planets' atmospheres into audible sounds. That's how astronomers found out that Neptune sounds like ocean waves, Jupiter like being underwater, and Saturn's voice resembles background music to a horror movie. Here on Earth, it's bebop jazz. No, I made that up. The sun's surface is scorching hot, but a bolt of lightning is 5 times hotter. Earth gets struck by 100 lightning bolts every second, which results in 8 million lightning strikes a day and around 3 billion a year. Ooh, shocking. If you manage to go to the moon one day and see fresh footprints, that doesn't mean there's someone else there with you. Footprints or similar marks can last for 1 million years over there. Because the moon doesn't have an atmosphere, there are no winds, not even a breeze, that can slowly erase those footprints. Astronomers have found the largest hole we've ever seen in the universe. It's the giant void that spreads 1 billion light-years across. They found it accidentally. One of the research team members was a little bored and wanted to check how things are going in the direction of the cold spot. That's an anomaly in the Cosmic Microwave Background Map, or CMB for short. It's a faint glow of light that falls on our planet from different directions and fills the universe. It's been streaming through space for almost 14 billion years as the afterglow that occurred after the Big Bang. So you fall right into the heart of the black hole and prepare for a sad end. Well, you don't have to. Falling into a black hole won't necessarily destroy you or your spaceship. You have to choose a bigger black hole to survive. If you fall into a small black hole, its event horizon is too narrow, and the gravity increases every inch down. So if you extend your arm forward, the gravity on your fingers is much stronger than on your elbow. This will make your hand lengthen, and you'll feel some discomfort. Rather significant, to be honest. Things change if you fall into a supermassive black hole, like the ones in the center of galaxies. They can be millions of times heavier than the Sun. Their event horizon is wide, and the gravity doesn't change as quickly. So, the force you'll feel at your heels and at the top of your head will be about the same. And you can go all the way to the heart of the black hole. This myth is busted. If you watch a very touching movie in space and start crying, your tears won't run down. They will gather around the eyeballs. Your eyes will get too dry, so you'll feel like they're burning. Any exposed liquid on your body will vaporize, including the surfaces of your tongue. Speaking of burning, that's one thing fire can't do in space. Fire can spread when there's a flow of oxygen, and since there's not any in space, well. Once they explode, stars aren't supposed to come back to life. But some of the stars somehow has survived the great supernova explosion. Such zombie stars are pretty rare. Scientists found a really big one called LP 40-365. It's a partially burnt white dwarf. A white dwarf is a star that burned up all of the hydrogen, and that hydrogen was previously its nuclear fuel. In this case, the final explosion was maybe weaker than it usually is, not powerful enough to destroy the entire star. It's like a star wanted to explode but didn't make it, which is why part of the matter still survived. If you ever go into space, don't take off your spacesuit unless you're on a spaceship. Air in your lungs would expand, as well as the oxygen in the rest of your body. You'd be like a balloon, twice your regular size. Good news, the skin is elastic enough to hold you together, which means you wouldn't explode. Small comfort. When something goes into a black hole, it changes shape and gets stretched out just like spaghetti. This happens because gravitational force is trying to stretch an object in one direction, but at the same time squeeze it into another, like a pasta paradox. Speaking of, a black hole that's as big as a single atom has the mass of a really big mountain. There's one at the center of the Milky Way called Sagittarius A. It has a mass like for 1 billion suns, but luckily it's far away from us. If you made a big boom on an asteroid, you'd never be able to hear its loud sound. Yes, we often hear the sound of spaceships and battles in space in the movies, but that's just a myth. Sound is a wave that spreads because of the vibrations of molecules. A person claps a few feet away from you, the sound wave begins to push the first air molecule next to the clap, then the second, third, and so on, until the wave reaches your ear. So, to spread sound, we need molecules like air or water. In our atmosphere, sound waves spread out just fine, but space is a vacuum, so it's nothing here. You can clap your hands loudly there, but there just won't be any molecules that can vibrate and carry that sound. So, to carry on a conversation, you'd either need a radio or really good lip-reading skills. Meteoroids orbit the Sun, while the majority of human-made debris orbits our planet. For example, we launched almost 9,000 spacecraft around the world from satellites to rocket ships. Even the tiniest pieces can damage a spacecraft at such high speeds. Galaxies, planets, comets, asteroids, stars, space bodies are things we can actually see in space. But they make up less than 5% of the total universe. Dark matter, one of the biggest mysteries in space, is the name we use for all the mass in the universe that's still invisible to us. And there's a lot of it. It may even make 25% of the universe. Dark energy makes the other 70% of the universe. That adds up to 100, right? Now, let's look at the moon. It always looks at us with one side. This means the moon has a dark side and the sun's rays never get there. Well, that's a myth. The whole point is that the moon is gravitationally locked to the Earth. There are days and nights there too. It's just that this rotation is perfectly aligned with the rotation of the Earth. So whenever you look at the moon, you only see one side. Although there are days when the sun shines there too, so it's not the dark side, it's the far side. And we even have pictures of this place. And there's one of the biggest craters in our entire solar system, the South Pole Aitken Basin. It's as wide as 2 states of Texas. Yeehaw! One myth that turned out to be untrue is that people have never actually been on the moon. This is the original spacesuit of the first astronauts who were there. Look at the sole of the shoe. Some people claim there's no way they could have left footprints like this there. Actually, they could. On the moon, the astronauts wore extra boots over their suits, and their soles matched the footprints on the moon perfectly. Now, the astronauts didn't need them when they left the moon and tossed them when the moonwalk was over. They left a lot of stuff there, too. They even tossed the armrests of the seats in the lunar module to reduce the weight. Now, counting all the Apollo lunar missions, the total weight of rubbish on the moon is approximately 187 tons, including several lunar rovers, spacecraft debris, 6 lunar modules, and all the experiments left behind. That's like 3 Boeing 737s. Another myth about the sun is that it's yellow. Let's send you into space for this one. You look out the window and it's white. The sun only appears yellow to us through the filter of our atmosphere. The composition of the air and its thickness just distorts the light of the star. But stars do come in different colors. Cooler stars have bright orange and red colors. These are usually very old stars, older than our sun. But young and very hot stars are bright blue. The sun is about in the middle of this spectrum. Oh, one more myth about asteroids. We need to fly a little farther than Mars's orbit. Whoa, we're in an asteroid belt, and we constantly have to dodge giant rocks and blocks of ice. We got in some dense asteroid clouds. Not true. The fact is that space is huge, and the distances are incredible. All the rocks and debris in the asteroid belt are only 4% of the weight of the moon, so there really aren't that many of them there. To understand the dimension of the emptiness in space, look at the collision of 2 galaxies. There are billions of stars in each of them. If we mix them up, it's unlikely there will be any collisions even here.
Aristotle once said that gold was water solidified in the ground and mixed with the sun's rays. Others were sure that gold was made with the help of the philosopher's stone. When the ancient Incas first saw gold, they decided that this metal, falling from the sky, was the tears of a mythical creature, but its real origin seems much more epic. Let's go to a very distant past, to the time when there were no people or animals, to the time when dinosaurs didn't exist yet, to the era when the simplest forms of life were just being formed. Our planet resembled a huge cauldron of chemical elements. There were erupting volcanoes, earthquakes, and lightning flashes all the time. It was about 3.9 billion years ago. During this period, huge asteroids flew through our solar system. They fell on Mercury, Venus, Earth, and Mars. It's possible that asteroids also fell on the moon and left large craters on it. There was a real apocalypse on our planet. But fortunately, no one felt it because there was no life yet. Along with the destruction, the asteroids brought metals. But were there metals on Earth before that? Of course. The core of our planet is mainly made up of metals such as iron. From there, it spreads to Earth's crust, mixes with magma, comes into contact with oxygen, and combines with other elements. But how did they get into the core? Simple hydrogen and helium atoms merged and formed heavier elements inside giant stars. Then, supernovae exploded and formed big clouds of dust and gas. These clouds reached our galaxy and began to revolve around the sun. Over time, this dust and the remnants of stars formed planets. One of them was our Earth. Metals lying in the bowels of our planet are difficult to get, and we wouldn't have the technology we have now if it wasn't for that meteor shower that left metals on Earth's surface. There are two theories. The first suggests that powerful supernova explosions far from our universe formed a lot of metals from the periodic table. During the explosion, nuclear fusion started, and it created atoms of gold. Then the blast wave threw those hot pieces in different directions. They flew for a long time, cooled down in cold space, and reached our solar system. Another theory says that gold and other metals appeared because of the merger of two neutron stars. These are powerful giant stars that are many times smaller in size than the Sun, but several times heavier than it. These are objects with tremendous gravitational force and density. Their collision formed an intense gamma-ray burst of radiation that could synthesize gold. In 2017, astrophysicists observed the collision of two neutron stars for the first time. They found traces of heavy metals, including gold, using gravitational wave detectors. So this theory seems more likely. And what if we go even further? Where did stars come from? Clouds of dust and gas are scattered throughout the universe. They mix, combine into one mass, and grow like a snowball. They squeeze each other and form a gravitational force. When all the material collapses, it starts to heat up, and then this surge of energy creates a star. Some physicists assume that stars, during their lifetime, can produce most of the elements of the periodic table. If this theory is true, then our body also consists of stars. We may be part of some gigantic supernova that exploded billions of years ago at the other end of the universe. More than 50 years have passed since the appearance of this theory, but no one has proved or disproved it. Okay, let's get back to gold. One of the largest gold deposits in the world is in southern Africa. Scientists believe that the precious metal appeared there more than 2 billion years ago after the fall of a giant meteorite. People are sure that gold is hidden in the world's oceans. Anywhere from 10 to 20 million tons of this precious metal can be underwater. But those are not large stones, but tiny particles dissolved in liquid. The extraction of such gold is too expensive. Now, let's find out how people mine gold and turn it into jewelry. At first, people find gold deposits, large plots of land or rock inside which gold is hidden. Workers begin to use picks, shovels, and machines to extract shiny pieces from the rock. Then these pieces are dissolved in a special acid that separates the gold from the solids. After that, other substances get removed from the precious metal by melting or using gaseous flora. When the gold is purified, it's checked for purity. 99.9% is the benchmark. Done. Your gold is ready to use. You can turn it into jewelry or part of an electronic device. The rarest metals on Earth also got here from stars. I'm talking about rhodium and iridium. They are several times more expensive than gold, not because of their beauty, but because of their practical value. For example, rhodium and iridium can turn harmful gases into harmless ones, and 90% of the demand for this metal falls on the automakers market. People use these metals in the manufacturing of auto catalysts. They are needed to clean harmful exhaust. When toxic substances produced during fuel combustion come into contact with these precious metals, they become their safer forms. A micro-layer of rhodium and iridium is applied to the walls of the catalyst cylinder. Gold, platinum, rhodium, and iridium are the most expensive metals. But what about the most durable ones? It's a little complicated to determine one winner because the strength of a metal depends on 4 criteria. First, there's tensile strength. This is the ability of a metal to resist tearing. For example, modeling clay has a low tensile strength because you can easily stretch it in different directions. Among metals, tungsten is perhaps the most difficult to stretch. Another criterion is compressive strength. This is the ability of a metal to resist compression. And here, chrome is one of the strongest. The third criterion for the strength of metals is yield strength. To test this, you need to make a rod or beam from any metal and then try to bend it and break it. The metal that shows the greatest resistance has a high yield strength level, and titanium is pretty good for that. And the fourth criterion is impact strength. This shows how strong the metal is when it gets dropped or hit. In this regard, iron shows a good result. Each metal has its own strong and weak sides. Chrome, for example, has a high resistance to compression, but it's weak if you try to stretch it. Therefore, people make metal alloys to combine their strengths. Okay, we've learned about the rarest and most expensive metals. And what about other elements? What's the rarest substance in the world? Meet astatine, the rarest element on the planet. There are about 0.8 ounces of this substance found in the whole world. The rate of its decay is equal to the speed of its formation. Therefore, the amount of the substance in nature doesn't change. People discussed it in the 1800s and discovered it at the end of the 19th century. But even now, after so many years, we know little about this element. In 1869, the creator of the periodic table, Dmitri Mendeleev, learned that there was a certain substance numbered 85 in the group of halogen elements. This group of nonmetals includes such substances as fluorine, chlorine, bromine, and iodine. So astatine is considered the heaviest of all known halogens and most similar to metals. It has a low melting point and conducts heat and electricity poorly. It's brittle in solid form and has a dark color. Even today, scientists don't know all its properties. It's almost impossible to find it in nature, but chemists have learned to synthesize it artificially. People don't know how to use this element because it's too radioactive. But in some laboratories, scientists conduct experiments using astatine to treat thyroid diseases.
Traveling at about 17,000 miles per hour, 250 miles above the Earth, astronauts watch 16 sunrises and sunsets every day while floating around in a box with a handful of people they depend on for survival. Whether humans should set off to other worlds beyond Earth or not, one of the most compelling drawbacks is this: our bodies don't like it. Few people know this better than the NASA astronaut who spent nearly a year on the International Space Station from 2015 to 2016, Scott Kelly. Like other astronauts, Mr. Kelly served as a test subject in the study of space travel's effects on the human body. Unlike other astronauts, Mr. Kelly has an identical twin, Mark, who is an astronaut himself. This gave researchers an uncommon opportunity to monitor the two brothers as they lived in two very different environments, one on Earth and the other 250 miles above it. When the astronaut went into space and his slightly older twin brother Mark stayed on Earth, the age gap between them increased thanks to his time in orbit. And it's all down to Einstein's theory of relativity. What it suggests is that time moves more slowly for objects in motion than it does for a stationary observer. It also moves more slowly the closer you are to a gravitational mass like Earth. In other words, we're not all experiencing time at the same rate. The faster you move and accelerate, the more time slows down. And because Mr. Kelly has been zooming up to and down from space and orbiting the planet at around 17,500 miles per hour, his brother Mark has lived through 0.005 extra seconds. The brothers were born 6 seconds apart back in 1964, and now that gap is 6.005 seconds. This warping of time is known as time dilation, and the Kelly brothers qualify for both aspects of it: how fast they've been moving in relation to one another and how close they are to a big object, which is Earth. So, depending on our position and speed, time can appear to move faster or slower to us relative to others in a different part of space-time. And for astronauts on the International Space Station, that means they get to age just a tiny bit slower than people on Earth. That doesn't mean you could spend your life in a basement just to outlive the rest of us here on the surface. The effect isn't noticeable on such a small scale. If you became a basement hermit, then across your entire lifetime, you'd only age a fraction of a second slower than everyone else above ground. But your brain might freeze when you think about this. A watch strapped to your ankle will eventually fall behind one strapped to your wrist. Your head technically ages more quickly than your feet. Time passes faster for people living on a mountain than those living at sea level. The classic example for this is the twin scenario. One twin blasts off in a spaceship, traveling close to the speed of light, and the other stays behind on Earth. When the space-traveling twin returns to Earth, she's only aged a couple of years. But she's shocked to find that her Earthbound sister has aged over a decade. Of course, no one has performed that experiment in real life, but there's evidence that it's real. When scientists launched an atomic clock into orbit and back, while keeping an identical clock here on Earth, it returned running ever so slightly behind the Earthbound clock. Then time gets even more complicated, because time dilation can happen anytime. A good way to think about it is to consider the astronauts living on the International Space Station. They're floating about 260 miles above where Earth's gravitational pull is weaker than it is at the surface. That means time should speed up for them relative to the people on the ground. But the space station is also whizzing around Earth at about nearly 5 miles per second. That means time should also slow down for the astronauts relative to people on the surface. But the reality is that Mark, the brother who's aged a few milliseconds longer, could end up better off in the long run if Mr. Kelly's extended time in space causes his body to deteriorate faster. 10 science teams in NASA's twin study examined the brothers' astronauts before, during, and after the astronauts' 340 days in space. The teams studied each twin's bodily functions, they ran memory tests, and they examined the men's genes, looking what differences might be due to space travel. They confirmed that lengthy space travel stresses the human body in many ways. Space living can change genes and send the immune system into overdrive. It can dull mind and memory. Most changes that the astronaut experienced in space reversed once he returned to Earth, but not everything. The researchers tested him again after 6 months back on land. Roughly 91% of the genes that had changed activity in space were now back to normal. The rest stayed in space mode. His immune system, for instance, remained on high alert. DNA repair genes were still overly active, and some of his chromosomes were still topsy-turvy. What's more, the astronaut's mental abilities had declined from pre-flight levels. He was slower and less accurate on short-term memory and logic tests. It's unclear whether these results are definitely from spaceflight. That's partly because the observations are from only one person. But one thing is sure, time is relative. Think of it this way. If a clock is stationary and you are traveling at a very high speed, you happen to pass by this clock and have a glimpse at it, you'll see that it's running slowly, or maybe it's completely static. This is because the speed at which the mechanical functions of the clock are working slower than you. What you see is the time in the past, while you have already skipped that second and are in the future. During this experiment of high-speed traveling, you haven't aged at all, because all the processes in your body are working at the same speed as you. After a certain age, your body starts to deteriorate, which eventually leads to a state when it stops functioning. This aging phenomenon, especially in humans, is caused by a protein structure in the cells called telomeres. These structures protect our cells from deteriorating, but with each cell replication, these telomeres start to lose strength, which is called telomere length. If the telomere length shortens to a certain extent, the cell becomes vulnerable to diseases. We can say that telomeres are the natural countdown timers in our bodies, which determine when we will expire. The telomere length can be affected by external factors like stress, which accelerates our timer. The twin study experiment by NASA included documenting the changes in telomere length of both brothers. The telomere length of the space brother increased while he was aboard the International Space Station. Before the mission, both brothers had nearly the same telomere lengths, meaning if we ignore issues like mental stress, both brothers should live roughly an equal age. But while the space brother was orbiting the Earth, he had almost 14.5% longer telomere length. The space brother was a few years younger than his ground brother biologically. Because the telomere length of the space brother resumed to normal when he came back to Earth, it took almost 190 days after return for the telomere length to restore to expected. The blood samples from the International Space Station were sent back to Earth for processing. This means the blood wasn't traveling at the speed of the ISS anymore. Also, the space-time paradox states that the space brother should be younger upon return. But the telomere length restored to its original state before the mission. The space brother was again the same age as his ground brother. A lack of gravity is the main cause for these intense changes in aging. Gravity plays an immense role in the majority of our bodily systems. Take the muscles, for example. Older people's muscles tend to shrink and decline as they age and become less mobile. Astronauts' muscles react in a similar way because they are barely used. That's why astronauts staying in space for extended periods of time use special exercise machines to help reduce this effect. A similar process takes place in the bones. After a certain age, people on Earth start to lose mass in their bones, typically at a rate of about 1 to 2% a year. But in space, those people lose bone mass at a greatly accelerated rate, as much as 1 to 2% a month. Because the astronauts' bodies don't need to support their weight, the bones begin to decrease production of new bone material and increase the amount of old bone absorption. Luckily, their skeletal systems usually return to normal once they've spent some time back on our blue planet. If the space brother was shielded from all harms of space, like radiations, while orbiting the ISS, then he would have lived longer than his ground brother. Even though they're saving 0.005 seconds, astronauts still experience some of the symptoms of a drawn-out aging process. So the next time you find yourself wishing the weekend would last longer, stay low to the ground and move really fast. It won't feel like your weekend got any longer, but technically, you may gain a teeny tiny fraction of a second. You won't need to go to space for this little experiment.